Compare these two environments. On the left, a single line of PyTorch code. Device equals CUDA. On the right, the physical reality, a dense silicon die containing tens of billions of transistors. Deep learning frameworks use software APIs to separate the developer from the underlying hardware. This layer of abstraction ensures that complex tensor operations are managed automatically, hidden behind high-level Python syntax. While convenient, this creates a knowledge gap. Engineers cannot effectively optimize training efficiency or resolve memory bottlenecks without understanding the physical layout of the silicon executing the instructions. To bridge this gap, we must examine how GPU design diverges from traditional CPU architecture. A CPU is built for serial precision. It allocates significant die space to complex control logic and deep caches to ensure that a single thread of execution can complete sequential, logic-heavy. A GPU ignores serial complexity to prioritize throughput. It packs thousands of simplified arithmetic units onto the silicon, designed to execute a vast number of parallel tasks simultaneously. Understanding AI performance requires building a conceptual GPU from the ground up, starting with a single computational thread and scaling into an extensive hardware array. At the base of the architecture is the thread. This is the smallest unit of execution, equipped with its own program counter and a local set of memory registers. Although threads can hold independent data, NVIDIA hardware never schedules them individually. Execution always happens in fixed groups. NVIDIA hardware binds exactly 32 threads into a single execution unit called a warp. For comparison, AMD's architecture uses a 64-thread grouping called a wavefront. Both vendors use these rigid blocks as the primary unit of scheduling. This is the single instruction multiple threads, or SIMT model. Every thread in this warp receives the same instruction at the same clock cycle, applying that instruction to 32 different data points in parallel. This model fails when threads within a warp encounter different logical paths, such as an if-else statement. Because the hardware cannot execute two different instructions at once, it serializes the paths. Half the warp idles while the others process path A, then they swap. This warp divergence penalty is a fundamental bottleneck. High-performance GPU code must keep parallel threads synchronized to prevent the hardware from stalling. Warps are organized into larger logical structures called thread blocks. These can contain up to 1,024 threads working on a shared subset of a problem. This hierarchy allows threads within a block to communicate through shared local memory and synchronize their progress at specific execution barriers. The hardware unit responsible for executing these blocks is the Streaming Multiprocessor, or SM. This is the fundamental engine of the GPU. A single high-end chip contains an array of over 100 identical SMs. The primary goal of each SM is to ensure its execution units are never idle, constantly processing new mathematical operations. The main obstacle is memory latency. When a warp requests data from the global VRAM, it takes hundreds of clock cycles for those numbers to arrive, leaving the warp stalled. The SM manages these delays through a hardware warp scheduler. When one warp stalls to wait for memory, the scheduler instantly context switches to a different warp that is already loaded and ready to compute. GPU performance relies on the scheduler's ability to mathematically mask the time spent on data transit by saturating the execution pipeline with ready warps. Traditional math within the SM is handled by CUDA cores. These units are versatile, handling 32-bit arithmetic for general computing and 3D graphics. Deep learning, however, is driven by a single repetitive operation: matrix, multiply, and accumulate. Starting with the voltage generation, NVIDIA began a fundamental architectural pivot. They reallocated silicon die space from general CUDA cores to specialized blocks called Tensor Cores. These units sacrifice logical flexibility to execute dense matrix math. By hardwiring these operations into the silicon, Tensor Cores process neural network layers at speeds far exceeding general-purpose units. Beyond specialized silicon, manufacturers accelerate AI through reduced mathematical precision. High-precision 64-bit and 32-bit formats have been replaced by custom AI types. The Ampere architecture introduced TensorFloat 32, a 19-bit format that maintains the range of 32-bit math while significantly reducing the computational load. The Hopper architecture introduced the transformer engine, which dynamically switches between 16-bit and 8-bit precision. It selects the lowest bit width possible for each specific neural network layer to maximize throughput. Blackwell continues this trend with FP4, a 4-bit precision format engineered to run trillion-parameter large language models with extreme efficiency. Scaling AI performance now depends on specialized matrix hardware running at the lowest bit precision possible without causing the model to collapse. The central bottleneck of modern hardware is data movement. Mathematical operations execute within a few nanoseconds, but fetching data across the silicon consumes hundreds of clock cycles. This is managed through a spatial memory hierarchy. At the top of this pyramid is the global VRAM. This holds the most data, often up to 80 gigabytes, but it is the furthest from the compute units. Data flows down into the L2 cache. This pool is shared across all SMs, providing a faster, closer buffer for frequently accessed data. Closer still is the L1 cache, or shared memory. This is local to each SM, allowing threads to access data within a handful of cycles. At the absolute bottom are the registers. These sit directly adjacent to the execution units and offer the highest speeds, though their capacity is limited to a single thread. NVIDIA and AMD take different approaches to managing the bandwidth at the top of this pyramid. NVIDIA prioritizes brute force VRAM bandwidth. The Blackwell architecture uses HBM3E memory to push over 4 terabytes of data per second into the die, supported by an ever-expanding L2 cache. AMD offsets narrower memory interfaces by embedding infinity caches directly onto the die. These massive on-chip buffers keep data physically closer to the compute units, reducing the need to access external VRAM. Success in AI training depends on mastering this hierarchy. Performance is determined by keeping data in the lowest, fastest tiers of the pyramid to avoid execution stalls. We can now map a standard training loop onto this physical reality. You define a model in Python, feed in the data, and initiate forward and backward passes. Software frameworks compile those matrix operations into optimized CUDA kernels using backend libraries like cuDNN, which are specifically tuned for the target architecture. The system triggers a memory transfer, pushing model parameters and input tensors from the system RAM into the GPU's high-capacity VRAM. During the initial kernel launch, distributed grids of thread blocks are dispatched to individual streaming multiprocessors across the die. Inside the SM, warp schedulers interleave instructions at high speed, hiding memory latency by constantly keeping the arithmetic units busy while the local caches fetch the next set of weights. Specialized tensor cores then execute the high-throughput matrix multiplications, rapidly processing the neural network layers using reduced FP16 or FP8 formats. The modern hardware stack functions as a specialized hierarchical matrix engine. Here, software performance depends entirely on mastering parallel concurrency and silicon-level memory proximity.